Good morning, everyone. Welcome to this second video lecture of this course. Today we're going to learn about growth of functions, and growth of functions are the mathematical tools which we're going to use when we're going to learn about algorithms and time complexity of the algorithms. In this chapter, we are basically going to focus on certain notations. So we're going to learn what do you mean by big O notations, what do you mean by big omega notation, and what do you mean by big theta notation. These notations will provide us a mathematical tool to analyze the algorithm. The concept of a big O notation was given by Paul in 1892. Paul was a Swiss mathematician, and then the growth of the functions and this big O notation was used in mathematics in the area of number theory by Landau. He was a German mathematician. And Donald, who was a computer scientist as well as a mathematician from Milwaukee, he developed this idea how to use this big O notations in analyzing the time complexity of the algorithm. These notations has a particular application in mathematics in the area of number theory and cryptography. But in computer science, if you want to understand how quickly an algorithm can solve a problem for a given input size, so we can compare the efficiency of two different algorithms which are solving the same problem in deciding which one is the better efficient algorithm. We can also determine whether it's practical to use that particular algorithm as the input size grows. So you might have heard some algorithm which is a linear time complexity, and you want to avoid those algorithms which becomes difficult to execute based on their input size. First, we're going to build the concept of growth of the functions in computer science. So the first point about the growth of the function is it can be determined by using the highest order term present in your given function. So let's suppose if I take an example where I have three functions: f of x is equal to x square, g of x is equal to x square plus 2, h of x if I define as x square plus x plus 1, then I can see that for a small value of x, when x is equal to 1, my value of f of 1 is 1, f of g of 1 is 3, and h of 1 is also 3. But if I increase my value x from x is equal to 1 to x is equal to 10, then you see the value will grow. For f of 10 becomes 100, g of 10 becomes 102, h of 10 becomes 111. If I further increase the value of x to, let's suppose 100, then my f of 100 is 10,000, my g of 100 is 10,002, and my h of 100 is 10,101. So what did we learn here? So we learned even though f, g, and h, those are three different functions, but these three functions, they grow with the same rate, and where this largest order term, x square, is the term which is going to dominate the growth of those three functions. Okay, so we can conclude that for a growth of the function, the small order term like the term here, the two terms here in this function g of x, the small order term like x plus 1 here in this function h of x, they are not playing a role in the growth of the function. So only the highest order term present in any given example, that's going to dictate the growth of that function. So we saw our first example. Okay, let me put as example 1, where the lowest order term is not going to play a major role in deciding the growth of that given particular function. The growth of the function is always going to be based on the highest order term present in that particular function. Now we're going to look at the second example, and in the second example we're going to learn that a constant multiple of this high order term is not going to play any role in deciding the growth of the function. So if you look at the second example where I define my f of x is equal to x, so the coefficient of my highest order term is 1 here. If I define my g of x as 3 of x, the coefficient is 3 here. If I define my h of x as x divided by 5, then my coefficient of the highest order term, which is the linear term here, is 1 by 5. If I plot these three functions, so this is the graph with respect to my f of x, this is the graph with respect to my g of x, and this is the graph with respect to my h of x. So what I can conclude from these three figures, I can conclude that here f grows as fast as the another two functions g and h, so their growth is linear. So essentially we are only concerned with the shape of those functions. We are not concerned with the coefficient of the highest order term, because it's not important here in deciding the growth of this function. For this example of f, g and h, even though my function was x, 3 by x and x by 5, but I know all these three functions, they have the linear growth with respect to the x. So finally, I developed this concept that when I'm going to decide the growth of the function, then this lowest order term and the coefficient of the highest order term is not going to play any role in deciding the growth of that function. So the growth of function is always going to dictate by the highest order term present in that expression. So finally, I take an example. Okay. So in this example, if I have defined my f of x as x square, g of x as 2 times of x square plus 5 of x, and h of x as 100 times of x square plus 10 of x plus of 6, then how these three functions behaves for a large value of x, they're going to dictate the growth of these three functions. And based on my concept that this lowest order term here and the lowest order term here, they're not going to play a major role in deciding the growth of the given function, and the coefficient of the highest order term, they're also not going to play a role in deciding the growth of these three functions. So I can conclude here that for a large value of x, okay, this function f grows as fast as the other two functions g and h, and the growth of all these three functions, they are same, even my expression is different for all three of them. Using these concepts about the growth of the function, now I'm in the position to define my first notation, which is the big O notation. So the big O notation can be defined as, let's suppose if I define two functions f and g, and those two functions could be a function from a set of integer z to a set of real number r, or I can choose those function is defining from set of real number r to a set of real number r. So the point here is, if you decided to define those functions in general from a set of integers to a real number, those type of functions are mostly you will see in a computer science courses. If you decided to define those functions f and g from a real number to real number, so you will see this definition is mostly applicable to mathematics. Okay, so based on that, we can choose either to define from a set of integers to a set of real number, or from a set of real numbers to a set of real number. It depends on whether we are interested in the computer science or whether we are interested in defining them in mathematics in general. So we can define that if let f and g be functions from a set of integers or from a set of real numbers to a set of real numbers, then we say that the function f of x is big O of g of x if there exist two constants c and k such that the absolute value of f of x is less than equal to c times of absolute value of g of x whenever my value of x is greater than k. So this definition of the big O notation can be explained with the help of this figure. So let's suppose I have a function f of x which is defined here with this blue curve, and I have another function g of x which is defined by this red curve. Then can I find two constants c and k? So the constant c is here and the k is here, such that my f of x absolute value is less than equal to c times of g of x for all x greater than k. And since if we are talking about f of x, g of x as a time complexity function, which is mostly appear in computer science, so they are the function based on your input size, so they are always going to be a positive function. So in that case, particularly in the area of computer science, we just get rid of this absolute value. You can even say if f of x is less than equal to c times of g of x, because we are only talking about the positive functions. For every x greater than k, that's going to be my definition of if and only if f is big O of g. Okay, so it has a meaning that if you compare these two curves, f of x and g of x, then you see that this g of x function lies below than this f of x function. But once you can find a witness c, which if you multiply with your function g of x, then the growth of this function is going to increase, and it's going to go from this area, and it will go and cross your f of x at a particular point here, and that point is your x is equal to k. So you're saying that below that in this region, when x is less than k, your function f of x was bounding from above this function c times g of x. But once you cross this region, once you are in this region of x greater than k, then c times g of x is going to give the upper bound on this function f of x, and that's the meaning here, that this is going to be the upper bound of okay, on f of x. So for the big O notation, when we read that the function f of x is big O of g of x, it has a meaning. That means you are saying the function g of x is going to asymptotically going to dominate your given function f. And that's the meaning of this figure, that you can choose those witness c and k in such a way that this function c times g of x is going to asymptotically going to dominate your given function f of x. That means it's going to give the upper bound on this given function f of x. Okay, and these two constants c and k, usually in a computer science literature we call them as a witness to this relationship when you can claim that f of x is big O of g of x. You only required one pair of the witness, but in general there could be many pair of the witness which you can use to show this relationship hold between f of x and g of x. So for example, let's suppose my function f of x is a big O of g of x. That means I can find those witness k and c such that they're going to give me this inequality, that absolute value of f of x is less than equal to c times of absolute value of g of x for every x greater than k. And whenever such a witness c and k is possible, you can choose another pair of witness c prime and k prime such that c prime is going to be greater than c and k prime is also going to be greater than k. And then again you can hold this inequality, that if f of x is less than equal to c times of g of x, then with respect to those two new witness, you can say c times of g of x is also going to be less than equal to c prime times of absolute value of g of x, and whenever x is going to be greater than new witness value, which is k prime. Okay, so if one pair of witness exists, then you can find many different pair of witnesses for which you can claim that f of x is big O of g of x. The logic here is we required those kind of pair of witness which can give us the tight upper bound. Okay. Computer science literature, we have this slightly abuse of notation problem. So mostly in many textbook, you will see that the authors, they wrote that f of x is going to be equal to big O of g of x, instead of saying that f of x is big O of g of x. Okay, so this one is the correct notation, okay, of big O. So we cannot say f of x is equal to big O of g of x, because the meaning is going to be different. This is going to be slightly abuse of the notation. Okay, it is okay to write if you just want to say fx belongs to big O of g of x, because the big O of g of x is going to represent the set of functions that are big O of g of x. Okay, and the another thing which you will see in the computer science literature, instead of proving this inequality that f of x, absolute value of f of x is less than equal to c times of absolute value of g of x, usually you see them as f of x less than equal to c times of g of x, and this is because of the region, because the function is the positive functions. Okay, because the way they use this big O notation is mostly in time complexity of the algorithm, and time complexity of the algorithm depends on your input size, and your input size is always positive. Your complexity function is always going to be a positive function. Once you have the positive function, it doesn't matter whether you take the absolute value or whether you don't take the absolute value. So in a computer science literature, we don't take the absolute value. Okay. So only that much difference you see in the big O notation if you go to the mathematics literature or computer science literature. As k, such that I can satisfy this inequality that absolute value of f of x is less than equal to c times of absolute value of g of x for every value of x greater than k. Okay, so I'm going to show you two approaches, and by using this one of those approaches, you can find those two witness c and k which satisfy this particular inequality. In my first method, when I fix k equal to 1, then I have x is going to be greater than k, that means greater than 1. So you can conclude two things from there. If x is greater than 1, then x square is going to be greater than 1. Okay, just by taking a square. If x is greater than 1, we can also conclude from there that x square is greater than x. You can say multiply by x. Okay, so x is equal to x greater than 1 is going to give you two things. One is your x square is greater than 1, and another is your x square is greater than x. You can use this to get a bound on your f of x, which is your x square plus 2 of x plus of 1. You can say this is going to be bounded by x square plus 2 of x square plus x of square. Okay, which is basically equal to your 4 of x square. So somehow you prove that f of x is less than c times of x square, where your value of your witness c is equal to 4. Okay, and then by definition, f of x is big O of x square. My second method is based on the concept that I'm going to fix the value of c, and then I'm trying to find the value of k. If my function f of x is x square plus 2 of x plus of 1. Then from the concept of my growth of the function, I know that this x square is going to dominate the growth of this function. So since I have to prove that f of x is big of x square, so I can claim that, let's suppose this is less than 3 times of x square by choosing c equal to 3. Okay, so if I select my c equal to 3, then the only challenge is to obtain the value of k, and then I can claim my f of x is big of g of x. And you will see that this inequality is going to satisfy if I choose my k equal to 2, since so you say then k is going to be equal to 2, since f of x equal to x square plus 2 of x plus of 1 is less than 3 of x square whenever x is greater than 2. Okay, so this way you can fix the value of c, but just by looking the growth of the function and what you have to prove. And once you fix the value of c, then the challenge is here is to obtain the value of k, and you can easily obtain the value of k. You just start putting the value of k as a positive integer. So if you put x k equal to 1, so that means x is equal to 1, so this side is 1 plus 2 plus 1 is 3, this side is 3, they satisfy the equality sign. But if you put x is equal to 2, this side is your 4 plus 4, 8 plus 1, 9, and this side is going to be equal to your 12. So you satisfy this inequality whenever x is greater than 2. So it's up to you which method you want to use. I will always recommend my first method. You select the value of k equal to 1 and then try to find the value of c. This is the most easiest method here. Let's look at what this function is telling us graphically. So graphically you can see there are given function f of x, which is here. Okay, so the growth of this function is defined by this curve. The given function g of x is here, which is your x square. So right now my f of x is bounding from above my given function g of x for every value of x. But once I choose my witness c is equal to 4 and multiply this function g of x by witness c is equal to 4, this is my c times of g of x, then you will see the behavior of c times of g of x was initially it was bounding this given function f of x from below up to this region. Okay, up to this region of let's suppose this is x less than 1. So in the region of x less than 1, it was bounding this function f of x from the below. But once you go in this region of x greater than 1, that's going to bound this function f of x from the above. So you have a f of x is less than c times of g of x. So you will say this implies c times of g of x is bounding f of x from above. Or you can also say c times of g of x is an upper bound on f of x. Okay, so this is the meaning of big O notation. You are trying to find the upper bound on a given function f. There are some important facts about the big O notation. So you can look at in the example when your f of x is x square plus 2x plus 1, okay, and your gx is x square, and if you can prove that f of x is big O of g of x, and you can also show that g of x is big O of f of x, that means these two functions are of the same order. Okay, that means their growth are same, and we have seen this one before, that the growth of this function is x square and the growth of this function is also x square. So these two functions will be of the same order. The second important facts about the big O notation is if f of x is big O of g of x, and if you have another function h of x which is larger than your g of x for all positive real numbers, then you can conclude that f of x is a big O of this larger function which is h of x. Okay, and the proof is written here. So when you claim that f of x is big of g of x, that means there exist two witnesses c and k, and you can show this inequality that the absolute value of f of x is less than equal to c times of g of x for every x greater than k. And if I have my h of x function which is larger than my g of x, that means the absolute value of h of x is larger than g of x for all values of my x, then I can bound this c times of g of x by this inequality c times of h of x. Okay, and by using this factor I can say, since absolute value of f of x can be written as less than equal to c times of absolute value of h of x, I can claim my f of x is big O of h of x. Okay, so the one example of this problem, you can see it here. Let's suppose you have g of x as x square, f of x is this curve as x square plus x plus 1, and right now you can claim that f of x is big O of g of x. Okay, because c times of g of x could be, let's suppose, somewhere here. So after this value of k in this region of x greater than k, you can prove that that f of x is big O of g of x. But if we have another function h of x and f h of x is bigger than your g of x, then you can easily prove that this f of x is big O of h of x. Okay, but when we talk about the big O notation, we talk about the upper bound. So every function which is greater than this g of x, if you have the result that f of x is big of g of x, so every function h of x which is bigger than this function g of x is going to be satisfying this relation that f of x is also big of h of x. Okay, so there could be many different h of x exist, but we are only interested in finding the tight upper bound, and in that case, if I have to choose only one function which can bound my given function f of x from the above with a tight bound, then that function will be my g of x. Okay, let's look at another example, and this time we have to show that 7 of x square is big O of x cube. So if we fix our k equal to 7, then for x greater than 7, we have, if you just multiplying by x square to both sides, so this side will be your x cube is greater than 7 of x square. Okay, this you obtain by multiply of x square to x greater than 7 both sides. Agree? So we can say x greater than 7 implies x cube greater than 7 of x square. Okay, now if we choose k equal to 7 and c equal to 1, then by definition of big O, we have that 7 of x square is big O of x cube. So in our next example, we have to show that n square is not big O of n, and we can write the solution of this problem is by using our contradiction approach. So assume that n square is big O of n and see if we can find some kind of a contradiction there. Then by definition, there are constants c and k such that n square can be written as less than equal to c times of n whenever n is greater than k. So on dividing by n to the both side of n square less than equal to c times of n, we can conclude that n is going to be less than equal to c whenever n is greater than k, and this is a contradiction because this cannot be possible together. So this is a contradiction, and based on the contradiction approach, we have shown that n square is not big O of n. In this example, we have to prove the big O estimates for the polynomial of degree n. So let f of x is a polynomial of degree n, where f of x is written as a0 plus a1x plus a2x square all the way up to an x to the power n, where a of n is not equal to 0. This indication is going to be a polynomial of exactly equal to n. Then can you prove that f of x is big O of x of n? And in writing the proof of this example, we can use our first method. And in our first method, we first fix the value of witness k. So let's suppose my witness k is 1. That means I'm working under the case when my x is greater than k, and that means is the case x is greater than 1. Then we can have that absolute value of f of x is the same thing as equal to absolute value of this expression for the polynomial of degree n. Now if I use my triangular inequality, that the absolute value of a plus b is less than equal to triangular inequality, that the absolute value of a plus b is less than equal to absolute value of a plus absolute value of b to the right side of this first equation, then I can say the absolute value of f of x is going to be less than equal to absolute value of a of n x to the power n, absolute value of a of n minus 1 times x to the power n minus 1 plus all the way up to absolute value of a1 times x and plus absolute value of a of naught. Now since I'm working under the case that x is greater than 1, so from there I can conclude my x to the power n is greater than 1. I can also conclude or x to the power n is greater than x. I can also conclude x to the power n is greater than x square, or I can keep doing this one. I can say my x to the power n is greater than x to the power n minus 1. And using all those bound on the term of 1x square all the way up to x to the power n minus 1 on this right side, I can say this part of the inequality is bounded by absolute value of an plus absolute value of an minus 1 plus absolute value of a1 plus absolute value of a0 times x to the power n. Now from this inequality, I can choose this whole constant term as equal to a constant c, and then it's easy for me to show that absolute value of f of x is less than equal to c times of x of n whenever my x is greater than 1, and my constant c is the sum of the absolute value of all those coefficients of my polynomial of degree n. So I can claim that my f of x is big O of x to the power n. And that's the proof of this example. In my next example, I want to use the big O notation to estimate the sum of the first n positive integers. And my sum of the first n positive integers is nothing but 1 plus 2 plus 3 all the way up to n. Now I can show that this sum of the first n positive integer is going to be less than equal to n plus n plus n plus all the way up to n when my n is greater than 1. Okay, so this is going to be less than equal to, if you add those n number of times, this is basically equal to your n square. Okay, so I just saw it here that 1 plus 2 plus 3 all the way up to n is less than equal to n square whenever n is greater than 1. Okay, so if I choose my constant c is equal to 1 and k equal to 1, then with respect to these two witnesses, I can claim that by definition of a big O, 1 plus 2 plus 3, the sum of the positive n integer, is big O of n squared. Okay, so that's the solution of this example. In the next example, you want to use the big O notation to estimate your factorial of a factorial function, which is your n factorial. Now n factorial is written as multiple of 1 times 2 times 3 times all the way up to n, and I can easily show that this quantity is less than equal to n times n times n times all the way up to n whenever my n is greater than 1. Okay, so this side, when you multiply n number of times, is going to be your n to the power n. This side is your n factorial. Okay, so you have this inequality, and this is going to be true whenever your n is greater than 1. Then you select the constant c is equal to 1, the constant k is equal to 1, and using the definition of a big O, we get that n factorial is big O of n to the power n. Okay, so that's the result we have, that n factorial is big O of n to the power n. In my next example, I want to use the big O notation to estimate your log of n factorial. Now you can obtain the big O notation to estimate your log of n factorial. If you look at your previous example, then in our previous example we have that n factorial can be written as less than equal to n to the power n whenever your n is greater than 1. Then you can take the log of both sides. So this side will be your log of n factorial, and this side will be your less than log of n to the power n. And it's going to be true whenever n is greater than 1, which you can simplify as less than equal to log of n to the power n is going to be n log of n. So if you choose your constant c equal to 1, the constant k equal to 1, then by definition of big O, we get that log of n factorial, okay, is big O of n log n. So this is another important result. You can say log of n factorial is big O of n log n, and this is the way you can write the proof of it. So in this figure we are going to display the growth of different classes of the function. So we have chosen f of n as 1, log of n, n log n, n square, 2 to the power n, and n factorial. And this x-axis is your n, and the value of n is increasing starting from 2 all the way up to 8. And this is the value of your function, which is your f of n. Okay. So now you can see the difference in the behavior of those functions as n become larger, and you can say absolutely that after this particular value of n, so after k equal to 4, and in this region whenever you have n greater than k, which is 4, so based on my definition of the big O notation, if I want to put those functions in an increasing order, so you can put all those functions in increasing order, depends on their upper bound. Okay, depends on their upper bound. So based on the big O notation, their increasing order is the lowest function is 1, then log of n, then big O of n, then big O of n log n, big O of n square, big O of 2 to the power n, and big O of n factorial. Okay. So you can say that if n become large, then factorial n is the function which is going to grow. From here that if n become larger, then factorial n is going to be the function which is going to grow faster than any other given function. We also have some important results about the combination of the functions in terms of their big O notation. So our first result is if f1 of x is big O of g1 of x, and if f2 of x is another function which is a big O of g2 of x, then you can prove that if you combine these two functions together, then f1 plus f2 of x, their combination is big O of maximum of absolute value of these two functions. Okay. Similarly, you can prove the result that if f1x and f2x are both big O of g of x, then the combination of these two functions is also going to be big O of x. Okay. Another simple result, you can prove that if f1 of x is big O of g of x, g1 of x, f2 of x is big O of g2 of x, then their multiplication of f1 times f2 of x is also big O of g1 time of x and g2 of x. Okay, so I'm going to write the proof of the first case. The other two cases it can be followed similarly. So let's look at how you write the proof for the combination of two functions. So here, if f1 of x is big O of g1 of x, if f2 of x is big O of g2 of x, then you have to prove that the combination of f1 plus f2 of x is big O of maximum of absolute value of g1 of x and absolute value of g2 of x. Then you can apply the definition of your big O notation. You can choose those two constants for each big O function. So you have a c1, c2 and k1, k2 are 4 constant here, where my f1 of x is a big O of g1 of x. So I have a relation here that absolute value of f1 of x is less than equal to c1 times of g1 of x whenever x1 is greater than k1. And similarly, I can apply my definition of the big O notation that absolute value of f2 of x is less than equal to c2 times of absolute value of g2 of x whenever x is greater than k of 2. So this line is completely based on the definition of the big O notation, since this is given to you that f1 of x is a big O of g1 of x, f2 of x is a big O of g2 of x. Now if we want to analyze the case of combination of f1 plus f2, so f1 plus f2 of x, if you look at here, apply your triangular inequality, so you can say the absolute value of f1 plus f2 of x on your variable x, and then you can say by using your triangular inequality, you can say this function is less than equal to f1 absolute value of f1x plus absolute value of f2x. Now I can apply my definition of the big O notation, which is given in terms of f1 function and f2 function, and I can say this term is bounded by this term and this term is bounded by this term. So the overall combination of absolute value of f1 of x plus absolute value of f2 of x is less than equal to c1 times absolute value of g1x plus c2 times absolute value of g2x. Okay, so I have used this equation 1 here. Okay, so you can see using 1 here. Okay, and since you want to claim, you want to find a witness C, so let's suppose if I define my g of x, which is the maximum of absolute value of g1 of x and absolute value of g2 of x, then I can say this inequality is going to be less than equal to c1 plus c2 and absolute value of g of x. Now if I define my constant c as a combination of c1 plus c2, so I can say this c1 plus c2 times absolute value of g of x is going to be equal to c times absolute value of g of x. So I've shown my left hand side is less than equal to c times of absolute value of g of x whenever my x is greater than k, and k is going to be the maximum of these two variable values, k1 and k2. Okay, and then by definition of a big O, we get the result. Because my result was to prove that the combination of f1 plus f2 function is going to be big O of maximum of absolute value of g1x and absolute value of g2 of x, which I proved it here.